I just wrote down the name or the symbol for an element, magnesium-23. I'm going to tell you that magnesium-23 will undergo beta-positive decay. I want you to right now write the reaction for the beta-positive decay, the beta-plus emission of magnesium-23. What comes next in this equation? We've got a beta-positive particle, which is the same thing as a positron, right? It's the antiparticle of an electron. Which side of the reaction does that go on? The left side or the right side? Not? It goes on the right side. So we're going to have an arrow next. A beta-positive particle could be written like this, or for some of you may have chosen to write it like this. Doesn't really matter. It's exactly the same thing. Beta plus, positron, doesn't really matter. What else we got to have over here? Well, we got to make sure that we balance out the number of protons and neutrons and so on, the atomic number and the mass number here. 0 plus what is equal to 23? 23. Plus 1 plus what is equal to 12? 11. Good. Okay, I told you guys the other day the most common mistake that's probably made in this unit is to misbalance these equations when you're dealing with beta negative decay and beta positive decay. What a lot of people will do, especially in beta negative decay, is make a mistake adding the negative value. It doesn't happen quite so much with beta positive decay, but be careful because sometimes we mix it up with beta negative decay. It is 11, and if you look at your periodic table for an atomic number 11, I think you find that it's boron, I think, isn't it? Sodium. Okay, sodium, yes. Is there anything else produced here in the process? Yep. This is going to be a neutrino. An antineutrino, that's a neutrino with the line over top of it, would be produced if it was beta negative decay. If it's beta positive decay, it's going to be a neutrino. How many people got this right, including the neutrino? Okay, good, good. I want you to take a look at your data sheets for just 1 second here. In the bottom left-hand corner of your data sheet, you see some physics principles listed. There's 10 of them, in fact. It goes from uniform motion all the way through wave-particle duality. You're going to get a few questions on your diploma exam where you're asked to describe or to list which physics principle you used to solve the problem. Okay, in most cases, it's fairly obvious, although we'll go through a few examples of it over the next week and a half just so that we make sure that you're on the right track with that. This one may be a little bit less obvious, okay? I'm going to tell you that to solve what we just solved, there are 2 physics principles that we used. Can anybody identify for me one of the physics principles that I used to solve this problem? Looking through the list there. Tom? No, not conservation of energy. No. Yep. Good. Conservation of nucleons. A nucleon is a proton or a neutron. We have to make sure the number of protons and neutrons remains the same. We start off with 23 nucleons. We have to end up with 23 nucleons. So principle number 8 would be what I would use to make sure that I'm balancing the number of protons and neutrons, conservation of nucleons. Okay, what other principle did I use here besides conservation of nucleons? Mac? Good. It's conservation of charge. We have a charge here of 12, and that results from having 12 protons, right? Here we have a charge of 12. And that results from having 11 protons and 1 positron. Total amount of charge remains the same, so we're going to say that that would be principle number 7. So if you ever had a question like this and you had to describe which 2 principles you used, it would be principle 8 and principle 7. Which order did you do them in? Who really cares, right? Atomic number first, mass number first, doesn't really matter. Go ahead. That's a good question, actually. That's a good question. Yeah, I think you could make an argument for that. That's not what you want to put. If you happen to get a question like that, that's not what you want to put, but I do think that you can make an argument for that. I really do. Problem is, when you write a diploma exam, you can't make an argument for anything because nobody's listening to you, right? Except the answer that you put, right? But yeah, I think that's a good point. All right, let's do one more here, guys. Let's do one more. Let's say we've got, let's do 2 more, actually. Let's say we have carbon-14. It undergoes beta negative decay. Carbon-14 undergoing beta negative decay. Write that one down, please. All right, now that you've finished that, what comes next in this one? The arrow, right? The arrow has to come next because if we're talking about beta negative decay, then the beta negative particle has to go on the right-hand side. If we're talking about something like electron capture, like we had in one of the problems that we worked on yesterday, then it would be on the left-hand side, right? The reactant side, or the, what's the other name we call reactants? In nuclear physics, a reactant is a No, that's the product. The product would be the daughter nucleus. The reactant would be the parent nucleus, right? So the carbon-14 is the parent nucleus. It decays into something. First of all, it decays into a beta-negative particle. If it was electron capture, it would absorb an electron. You don't need to know anything about electron capture unless they describe it, right? But know that if you're not producing something, it's going to appear on the left-hand side. What else we got here? Well, using the law of conservation of nucleons, we would say that 0 plus 14 is 14. Using the law of conservation of charge, we would say minus 1 plus what? 7, good, is equal to 6. And I think when we do this, we find that that one's going to be nitrogen. Is there anything else there? Christian, what else do we got to make sure is there? Good, it's going to be an antineutrino. Neutrinos go with beta positive decay. Antineutrinos go with beta negative decay. Let's do one more. Let's say you've got uranium-235. And it's going to undergo alpha decay. Let's write that one out, please. If it's alpha decay, if it's anything decay, then whatever you're talking about is going to appear on the right-hand side. So if we've got alpha decay, we're going to have an alpha particle appearing on the right-hand side. Notice that in all three of these cases, I'm writing the particle that's decaying into first. It doesn't really matter about that. I could have written here nitrogen-14 plus a beta particle as opposed to the other way around. I just find it easier to write this smaller particle that's being released first, usually at least. So what else we got here? Using conservation of nucleons, we would say 4 plus 231 gives me 235. Using conservation of charge, we would say 2 plus 90 equals 92. And that works out to be thorium. What else is over here? Neutrino or antineutrino? Yep. Neither one. Good. Trick question. It's neither one. Okay, when you have alpha decay, it is what it is. It's done. Now, what you could have as a result of alpha decay is maybe a gamma ray being released, but we would make that a separate reaction. Okay, the nucleus is left in an excited state here, and sometimes when that nucleus is left in the excited state, it fires off a gamma ray to get back down to its normal state. We wouldn't include that, though, in the transmutation reaction that we're writing there. We talked about the gamma decay, the gamma ray occurring as a result of the nucleus being left in an excited state going back down to its normal state. Why does this happen? Why does beta plus decay occur? I'll give you a hint. It has to do with the energy. Okay, both of these, in fact, have to do with the energy of the nucleus versus this one, which has to do with the forces in the nucleus. What's the problem with the energy in the first one? You got too many of something. Yep. You got too many neutrons in the first. Sorry, no, you got too many protons. You're right. Too many protons in the first one. If you don't remember that, that's okay. You can figure that out, right? Look at what's happening here. We have 12 protons. Now we've got 11 protons. If you've written it out, you can see that you've gotten rid of one proton. All right, so what's happening then? A proton, because it's energetically unstable to have that many protons, is being converted to a neutron and a positron. Okay? To keep the law of conservation of charge, a proton, which is plus 1, is converted to a neutron and a positron, which add up to give me plus 1. This is energetically unstable as well. In this case, we have too many. We got 6 protons and 8 neutrons. Here we have 7 protons and 7 neutrons. What do we get rid of there? Caitlin, what did we get rid of there? We got rid of a neutron. So you don't need to necessarily remember that you have too many neutrons. Okay, you can look at your equation and say that we have too many neutrons, so we have to get rid of a neutron, change it into a proton. We had 6 protons, now we get 7 protons. A proton, by the way, and an electron in order to keep the law of conservation of charge. Finally, this one, how does this one produced? This alpha particle. It's not because we have too many protons or neutrons, leaving it energetically unstable, but rather it's because we have too many protons, which leaves us with too big of a repulsive force. The repulsive force is too big, so the nucleus is unstable. Okay, we release an alpha particle to improve the ratio a bit, and there we go. That's what we're left with. Good? Okay, one more little thing, and then we'll check over the homework that we had last night. Yesterday we talked about half-life, which we said is statistically the time that it takes half of a sample to decay. If we have a kilogram After one half-life, you've got a half a kilogram. And a half a kilogram of something else, right? Half a kilogram of what you started with, though. After two half-lives, you've got a quarter of a kilogram. After three half-lives, you've got 125 grams, and so on and so on and so on. After each half-life, you go down by a factor of 50%. We used two equations to describe what was going on there. The first one doesn't appear on our data sheet, but it's a pretty easy one to figure out. N, the number of half-lives, is equal to T over T1 half, the total time divided by the half-life. And secondly, the one that does appear on your data sheet, N is equal to N sub 0, 1/2 to the little n. Little n, of course, being the number of half-lives, N sub 0 being the starting amount, the initial amount. And that can be measured in whatever you want, right? Grams, kilograms, just a number, percent, decays per second, decays per minute, whatever you want, as long as it indicates an amount. N would be the final amount. And you can use whatever you want for that as well, as long as it agrees with whatever units you used for the initial amount. Okay, that's it. Those are my two equations. I just got to be able to use those two equations. There's a twist that occurs in one of these equations. We'll see what that is in a few minutes after we've gone over our homework problems. We had two questions for homework on page 814. Any issues with either of those two questions? No? All right, well, I'm going to go over number 2 then. It says tritium, which is a heavy version of hydrogen. Chemically, it's identical to regular hydrogen. Hydrogen normally has one proton, no neutrons. Chemically, it's indistinguishable from regular hydrogen, but it has a couple extra neutrons. So chemically, it can form water just like regular hydrogen can, and it forms it in the form of H2O. It's not H3O or H4O or anything like that. It forms H2O. But this water would be dramatically heavier, dramatically more dense than regular water would be, because you've got a couple extra neutrons for every atom of hydrogen that you have in there. Okay? Tritium is an isotope of hydrogen that's not nearly as common as the regular isotope of hydrogen, which is one proton, no neutrons. It says tritium has a half-life of 12.3 years. How much remains after 5 years? We're going to say N, the number of half-lives, is T over T1 half. So that's going to be 5 over 12.3. I think that works out to be 0.4065. No units because it's just a number of half-lives. Right? Well, now we go to find out how much remains after 5 years. N is equal to N sub 0, 1/2 to the little n. We're going to say we start off with 100 milligrams. We'll multiply that by 1/2 to the 0.4065. And we end up with 75. What should the units be for this? Not percent. The units should be milligrams. Now, as it turns out, because we started off with 100 milligrams, 75% of 100 milligrams is 75 milligrams. It works out. Okay, but if the initial amount was 130 milligrams, the number for percent would be different than the number for milligrams. Make sense? What if I threw this one at you? What if I said, what percent of an 86 milligram sample would remain? What would you make N0 then? What percent of an 86 milligram sample remains? There's a couple ways to do this, but what's the easiest way? What's the initial amount? If we're talking about what percent of an 86 milligram sample remains. Dom? You can make it 86 milligrams and solve for the final amount in milligrams and then find out what percent that was as compared to the initial amount. Yeah, that would work. What's an easier way to do it though? What percent of an 86 milligram sample remains? The initial amount could be 100%. That make sense? Because 86 milligrams is still 100%. If we want to find the final amount in percent, then why don't we just make the initial amount 100%? Okay, both ways work there. Okay, I got one more to throw at you here. And then we're going to move on to some new stuff. Let's say that we have whatever material that has a half-life of 10 years. A half-life of 10 years. And let's say that the initial amount is 50 grams. And let's say the final amount, the amount that we have left, is 12.5 grams. I want to find out how long that takes. Well, the first thing we're probably going to do is write down the equation that has a little t in it. N is equal to t over t 1/2. Rearrange that, and we get t is equal to n times t 1/2. But there's a problem here in that we don't know what little n is. So we got to find it. So we go to our equation, our other equation, we say n is equal to n sub 0 1/2 to the little n. Solve for a little n. There's two ways to do that. There's the logarithm method. What is it? Log of what? N over n sub 0 over log of 1/2, which when we do that works out to be 3. And then we turn around and say 3 times the half-life of 10 years is 30 years. There's my answer. It's the other way to do it. What's the other way to find a little n besides using logarithms if you don't like logarithms? Or if you've never seen them before in math class. It's the divide by 2 method. Little n and big N. After 0 half-lives, I've got 50 grams. 1 half-life, it's 25 grams. 2 half-lives, it's 12.5 grams. Oh, I made a mistake. I didn't actually punch that into my calculator. What should I have gotten there? 2. 2 times 10 is 20 years. When I'm down to 12.5 grams, I can see that that's taken 2 half-lives, regardless of whether I use logarithms or whether I use the divide by 2 method. Whatever you get, okay, wherever you get it from, plug it back into here and solve for the time. All right? How many people feel like in a question like this, they might use logarithms? How many people feel like they might use the divide by 2 method? Okay. Whatever works. All right, I want to go through one more little thing here on radioactivity before we move on to our next topic of fission and fusion. We've done lots of graphs this year, some of them in class, such as force versus time graphs, and then some of them in labs, graphs such as PF versus PI or 1 over DI versus 1 over DO. Sometimes some complicated graphs like sine theta 2 versus sine theta 1. In all of those graphs, we learned to analyze them by finding what the slope represented, taking an equation from the graph, taking an equation from our data sheet, figuring out what the slope and the y-intercept represents, and then dealing with it. We're going to see a graph today where we can't do that. This is a graph that curves downward, but never actually, with theoretical data at least, reaches 0. This is a half-life graph or a nuclear decay graph. We have n on the y-axis and we have t on the x-axis. Now you can see that n is in the units of counts per minute here. The amount of counts per minute, the amount of decays per minute that we have here. N could be in percent, it could be in grams, it could be in just a number. It doesn't really matter. It's going to be big N on the y-axis, and it's going to be t on the x-axis, whether it's in days or seconds or minutes or years. It's going to be t on the x-axis. The reason we can't deal with this graph the same way as we dealt with our other graphs is because this isn't a straight line. But the good news is, although it's harder to actually deal with if you actually have to get anything significant from it, it's not hard to do what we need to do with it. All we need to do with it is to be able to read an amount or a time, Jackie, directly off of the graph. So that means that regardless of what we're trying to find, we're going to either go up and over, or we're going to go over and down. For instance, if a question asks us to find the half-life of this material, we start off with 80 counts per minute. How much do we have left after 1 half-life? Okay, well, if we start off with 80, how much do we have left after 1 half-life? 40, good. If we want to find out how long it takes to go down to 40, which is the half-life, right? Then we're going to go to 40 and we're going to go over and down. Looks like 2 days is the half-life. No calculation involved there. It was just over and down. Maybe we want to find out how much remains after 6 days. How much remains after 6 days? Let's go to 6 days and go up and over. And it looks like the amount that remains after 6 days would be 10 counts per minute. So we can't deal with this graph the way we've dealt with other graphs, but that's okay, because the only things we're ever going to have to do with this graph are go up and over or over and down. Right now on your unit test, this is question number 1 on your unit test. Now, I told you I was going to take a few questions off, so that may end up being one that's taken off. I'm not sure yet. Okay, but as it stands right now, this is question number 1. You got to go either up and over or over and down. And I'll tell you, this question number 1, there's typically a fair number of mistakes made on it, not because people don't know what they're doing, but because people aren't careful. When you're going up and over or over and down, people just aren't reading correctly off of the graph. So just make sure that you're, like I said, if you know how to do it, make sure you don't make a stupid mistake like not reading it properly. Okay?